Eric, welcome, and we're looking forward to your talk.
Yeah, thank you very much. Good afternoon, everybody. I haven't done anything yet. Okay, so I work in AI for a very long time, but of course recently we have all these new things in AI, like CNNs and transformers. Not these ones, but we will come back to them. But keep that in mind, CNNs and transformers. So it all started with Alan Turing. You might know Alan Turing from the imitation game or the Turing test. And in 1950 he wrote a paper where he thought about whether a computer could be smarter than humans. But most importantly, for the development of AI, he thought about the separation of brain and mind. He considered the brain to be the hardware, like a computer that you have on your desk, and the mind as software. And he thought that we could mimic this software, and that meant that you don't have to consider the hardware. And this led to what I call, or what's generally called GOFAI, the good old-fashioned AI, which is the approach to AI based on formal logic. So trying to program a computer to store all kinds of human knowledge in terms of if-then rules. And because Turing and others had this idea of dualism, the separation of brain and mind, you could just focus on the software. And the idea was we could create intelligent computers by trying to program computers to play chess or to do other high intelligence tasks. And this is an example of how you can build a knowledge system. They were called expert systems, one of the great failures of the early days of AI, because the idea was there to focus on the development of a system where you put all the human knowledge in terms of if-then rules and apply the rules of logic to infer new knowledge. And this was on the old days of the AI, the big dream, and it failed. But there were some successes, like we had this world championship chess, and we had a very powerful computer that outperformed the world champion chess player. And this was based on search algorithms that you could consider to be a kind of AI. So that was AI, and of course there were lots of other things, but it was actually not so very successful. There was a kind of AI winter, because people were a bit fed up with AI. And one of the limitations was that NASA was planning on sending a robot to Mars, the Sojourner robot. And what you can see here is an animation that shows the communication speed when Mars is nearest to Earth. They wanted to send a robot to Mars. It had to navigate over Mars, and of course you had to avoid obstacles. And they wanted to give it some autonomous intelligence, because if you would remote control this robot, that by the time that Houston, which was controlling the robot, would see that it would hit a rock or something, it was already too late. And that's because the distance is enormous. Well, I won't wait until it arrives at Mars, but you can imagine once they see in Houston that the robot is about to fall in a cliff, it already happened. So they were asking the AI researchers to build intelligent robots that could sense the environment and help the robot to avoid obstacles. And all these AI researchers said, well, we can program it to play chess, but these kind of things we cannot do. So that was a clear limitation of AI. And this led to a new stream in AI, sometimes called symbolic AI, that focused on learning and where machine learning became important. And there was also a shift in from this dualist view, the separation of brain and mind, as the materialist view that said body is mind. So that's the kind of common assumption nowadays, also in neuroscience. And suddenly the knowledge about the human brain became important, and that helped us to be inspired by how the brain is working. And there was an emphasis on low-level cognitive tasks like pattern recognition. And I always show this slide as an example of pattern recognition. This is my dog. And my dog is an example of a non-rigid object, because you can put it in all kinds of shapes. Not all shapes, but many different shapes. For over 50 years, people in AI and in computer vision tried to build machines that could automatically label these pictures with the name of the dog or the breed of the dog or the fact that it's a dog. And it turned out to be very hard. They tried to build these 3D geometric models in the computer and then try to match that with dog. But this 3D model, geometric model, is very stiff, and this is a non-rigid object. Now, of course, it's not only about my dog, but also about many other important objects. But it was very difficult, and it turned out to be very hard. Now, we were kind of rescued, and that's the current deep learning hype or enthusiasm about AI, because we have now artificial neural networks. These are methods that are loosely inspired by how the brain is organized, very coarsely, in terms of neurons. You can also call it stacked logistic regressions, but you don't get funding for that. Or nested parameterized nonlinear functions. That's also not a very popular name. So what I want to emphasize, these neural networks are metaphors. And I have a simple bossable neural network here for you. This is one of the first neural networks. The idea, you have certain scores. So you're very hungry, and this is very typical if you are at yachts a lot. You're hungry, and you have a green arrow which indicates a positive influence on the outcome here. And the outcome is, should I eat this bossable or not? And the health score is, of course, a very negative weight. That's why it's red here. So you could say this is your neuron, and it's activated by hunger, but suppressed by your health considerations. And then there's the yacht score. It's gray, kind of intermediate. I don't know what the policy is at yachts. But depending on this and on learning, you can learn these weights from experience. So in the beginning, everybody ate was hungry and ate these bossenbollen, but after a few bossenbollen, you think it's not good for your health, and this might be bigger than this arrow. So there's a kind of learning principle behind neural networks. Now, people familiar with statistics see logistic regression here, and they're right. This is the logistic regression. But in artificial intelligence, it was called a perceptron, and this was about 1958. And this perceptron could learn automatically simple functions, but it was then taken over by this GOFAI that I just described. But in the 1980s, we had a research of interest in neural networks, the so-called multi-layer neural networks, which is a kind of stacked logistic regression. You have an input layer. These are numbers describing clients, or it could be pixel values of an image. You have a so-called hidden layer. These are kind of hidden variables. And an output layer that makes predictions. And all these lines here are parameters or weights, things that can change. Now, this was nice by the time, and you could solve very simple tasks, but I could still not automatically recognize my dog. And now since a year, about 10 years, now we have so-called deep neural networks, and the only difference is that they're much deeper. There's some other details, but they're not. And as they suggest, what it can do, you can put in the input layer an image, or actually the pixel values, but you put an image in. It's processed through this network, through all these parameters, all these connections. They all are initially randomly weighted, but after training, they all get specific values. And then at the end, you can automatically classify these images. Now, this training procedure is actually nothing new. It's a procedure. And for those of you who are interested, this is the neural network as it's typically shown, and this is the mathematics. So there's no mystery about how this works in the sense of how it operates and how you process images or signals or inputs towards the output. It's fully mathematically describable, but as you can see, quite boring. And so the intuitive notion is you have a big black box with a lot of knobs, and each of these parameters, each of these lines in this neural network are little knobs. And the idea is you put something in, and you look at the output. And if the output is correct, then you do nothing. If it's wrong, you change the knobs until it's giving the correct output. And you do that in small steps, which is a procedure known as gradient descent. It's from optimization, combinatorial optimization. Very old and well-known procedure, so nothing new there. Now, and with these neural networks, and here you now see CNN. It's a different CNN, convolutional neural networks. This was a breakthrough in image classification. So the idea is now you have a picture of a dog, and here you have all these breeds of dogs, and are being trained on a lot of examples of images with a label that says what the breed of the dog is, it can generalize to new images. So after training, it gets this image of my dog. Well, this is not my dog, but the same breed. And it can automatically classify it in most cases, let's say 95% of the cases, give it the correct label. And that's a breakthrough. That is nothing like human vision, because human vision works totally differently, but this is a very powerful classification method. And of course, we say that these neural networks recognize objects, but that's not entirely true. It's similar to recognition, but it's a different way of recognizing things. Now, one of the interesting things about this whole deep learning revolution is that, according to people in statistics, These are people in statistics, real scientists. And you have the AI researchers, more like pirates. Deep learning, because you have far too many parameters. All these knobs, it's a common principle in science that if you want to have an explanation, you should apply Occam's razor, which means that the number of knobs should be as small as possible to make predictions. But these pirates from my community, the AI community, they do everything that is forbidden, and they just try it out. And so they succeeded in building these forbidden models, and they turn out to be very successful. And we still don't know exactly why. And because they are AI researchers, they go on. They build new techniques like transformers. And a transformer is a system that is based on an attentional mechanism. So the inputs that you provide to the system are also attended. And it means that sometimes, so for instance, this is a common example from the language domain. If you have a sentence like the animal didn't cross the street because it was too tired, you have the word it, but it's also paying attention to other words. So as we do in language, it's not a single word that counts, but it's the combination of words that counts. And these transformers have an ability to attend that and to take that into account when encoding information. So these transformers are a kind of next step after convolutional neural networks. And so they are very powerful. And this is, for instance, seen in the so-called large language models. And you might have seen examples from this, like GPT. It's based on self-supervised training. So you provide it with text from the internet, for instance. You give it a part of a sentence, and it has to predict the next words in the sentence. Or you give it one sentence, and it has to predict the next sentence. This is called self-supervised learning because you don't need the labels. In this example with the dogs, you need images with a label, like this is a samoyed or this is a whatever. But here it's the text itself that is acting as the label. And these kind of systems that are not really very, electricity consuming things, so it's an enormous carbon footprint for these models. They are trained on huge data sets like the entire World Wide Web, Twitter feeds or whatever, even complete books. And they have a growing number of these free parameters. So the number of knobs is really going sky high. And as you can see, this is already from 2 years ago, but you can see one of the first had a very little number of parameters. You cannot even see it. It's in terms of billion parameters. This in 2019. In 2020, you see it's really boosting in the number of parameters, which might suggest that these models just simply store all the information, but that's not true. They really abstract information from the text. So they capture some, you could say, some meaning from the text. But what you can do now is have a conversation with these models. And there are many internet sites where you can do this yourself. So you can ask, what is your favorite animal? My favorite animal. This is this, and you might, how does this GPT know that that is the guess? Because he saw that a lot on the internet or something. And you can even ask for a motivation, and it gives a motivation because dogs are loyal and friendly, which is true in most cases. And what are 2 reasons that a dog might be in a bad mood? And it gives 2 perfectly valid reasons. So if you interact with these, and you think about these Turing tests, this is really convincing that these models have some intelligence. But of course they don't have that, because if you check it, you could say, how many eyes does a giraffe have? Well, a giraffe has 2 eyes, still correct. But then, how many eyes does my foot have? Your foot has 2 eyes. We would not make these mistakes. So these language models are very powerful. They are trained on much more material than we could ever be trained on. But they lack world knowledge, because they were not raised in a society in an environment like humans. And that's the difficulty with interpreting the power of these systems. They are not like humans. And we use words like humans if we describe these systems, but they're not like humans. So if you think about where are we now, we have narrow AI, which can help us to assist in scientific tasks and other specific tasks, or general AI, where you can take knowledge from one domain and copy it to another, or super AI, the machines that will take over humanity. Then we're just talking about narrow AI. The narrow AI is very, very powerful, but it is nothing which relates to general or superior AI. And that's one of the misleading things in many discussions about AI. It's simply a very powerful system that can almost learn anything, but it doesn't understand our world. So, but narrow AI is making great progress, and I illustrate that with one long-term project. Actually, I don't do this project anymore. I'm now working together with a company that tries to become rich with this. I'm not an entrepreneur, for those of you who didn't know that yet. So the idea is that once in, I think it was in 2000, we had the idea to build visual recognition models based on visual texture. And we were looking for a data set, and then when I was visiting the Van Gogh Museum, I thought, oh, I can maybe use paintings, because there's a lot of texture in these paintings, and I can maybe use that to classify textures or predict the author of the painting. And it turned out that that worked quite well. And this is an example of, do you know who the author is of this painting? Most people think it's a Van Gogh, but this is a fake. It's a Wacker forgery. And we were able to detect that. Actually, he uses too much of these Van Gogh-like things if you look at the data. But this is one of the examples. So this is an ongoing effort to try to use machines as a kind of digital connoisseur. Now, of course, any connoisseur, any art experts will tell you that it's not only the visual appearance of a painting, it's also the chemical composition of the painting and many other details. But we always saw that, personally, I was just interested in the pattern recognition. But if we try to explain that, this is more a support system for people analyzing paintings. Now, if you look at the CNNs that we just saw for this dog classification, what we see actually that the number of parameters is growing and that the accuracy is also growing. So here you see, for instance, EfficientNet is one of the latest CNNs. It has a lot of parameters in terms of millions of parameters, and it's growing and growing. And you see that the accuracy in general on recognition tasks is going up as well, which suggests that we as humans also have in our brain, we also have a lot of these parameters. These are the interconnections between neurons. So maybe there's a relation, but we're not sure. But at the same time, we also have these transformers that are behind these GPT models, but also now are making their entry in the visual domain. They're now also used for image classification. So I gave this example with a sentence, but also in images, it might be that something that is here is related to something that is there. And by these attentional mechanisms that you can use in these transformers, you can benefit from that, and that might give better results. Now, if I look at the development of the authentication accuracy on this data set, and I can say a lot about the validity of whether you really detect authenticity, but that's not the point here. It's about the pattern recognition power of these systems. You see actually that in the traditional machine learning, this was before deep learning, we achieved this level approximately. And now you see a steady increase since the introduction of CNNs and now transformers, vision transformers. You see a real boost in performance. So these models still become better in recognizing patterns and classifying these patterns. They do that in a greedy way. It's not the way that humans do that. And you should always take great care in interpreting these predictions, because these systems use anything that they can use. For instance, in terms of these dog classifications, if it happens to be the case that all images of these Samoyed dogs are in a white, snowy background, then these systems will also use that as a cue to make a prediction that that's a Samoyed, because it doesn't have to look at the dog, it just looks at the background. And this, of course, has to do with how good the data set is, and these kind of biases are easily introduced in AI systems, but also in humans. Don't forget that. So Chinese people that come to the Netherlands think that all Dutch people look alike. Dutch people that come to China say the same about Chinese people. This is the same problem as with biases in learning. So humans also suffer from these biases. Now, so I think in general, if you want to apply AI, you shouldn't talk too much about the ethical issues. I think there's too much discussion about ethical issues. I think you should address these, because you can use these models to see what kind of biases we have in our society. And that's what we are actually are doing. You can visualize where the biases are, and then think maybe we should change our policies rather than criticizing these models that are based on data that we created. So that concludes my presentation. There's now 10 minutes left for questions, by you, for instance.